of chapter 9, really almost half of chapter 9 last time. So we were talking about acids and bases, and then we talked about strong acids and bases. So remember, when you think of something that it's a strong acid or base, think of a strong electrolyte. So remember that that means that it forms ions 100%. Neutralization is a way of converting those strong acids and bases into a salt and water, right? So remember that, just think of it, that means that you're going from where you have lots of ions to having these neutral ions that are not corrosive. So remember, strong acids and bases have that characteristic of it being able to damage body tissues. But by adding them in equal parts, you can make a salt and water, like sodium chloride and water, and you end up having something that is neutral, not corrosive, not reactive. So if you take or start with a strong acid and a strong base, this looks like it's 10, so it's kind of back a bit. So just remember, strong acids and bases react and form a salt and water. That is called a neutralization reaction. So then from there, we went on, and I am not going to ask you to like complete a chemical reaction. Like if I gave this to you in a take-home exam, then I might, because you could look it up, but I am not going to ask you to finish a reaction. But remember, then I talked about antacids. Antacids are weak bases. So remember, a weak base is one that doesn't form lots of ions. So if it doesn't form a lot of hydroxide ions, it's not as corrosive. So this is why, like, you can eat a weak base. You can eat a Tums, you can eat a Rolaids, you can take baking soda, because those are weak bases, which means they don't make a lot of ions, but they can still help in neutralizing strong acids. So it helps to decrease the amount of stomach acid, and that's how it can relieve excess stomach acid in indigestion. So then that led us into the equilibrium part of the lecture. And this is when you have a forward and reverse reaction, because you have reactants to products and products to reactants, that there is some stability of reactants and products. So this is why the arrow doesn't go one direction. So in this, you would say, well, NH3, the product, is somewhat stable, but so are the reactants. And so that's why the reactants can form products, but then the products can act as reactants and break back down into the gases, the N2 and H3 as well. So when you reach equilibrium, remember that you have all of these present. So I actually have an example, okay, a demonstration to show you equilibrium. And it's really a way to look at what they call the K. So the reason that we do this demonstration is because K is a way of comparing the amount of products compared to the amount of reactants. So most of the time when people think of equilibrium, they think when you reach 50-50, right? If I have 50% reactants, 50% products, that's equilibrium, because I think I start off with 100, and so some of that forms product, and then when I get to about 50, now they're equal. Equilibrium does not necessarily mean I have the exact same amounts of reactants and products, but I can show you an example where this happens. So if the amount of reactant and product is equal at equilibrium, so if I have like a 50-50%, 50 reactants divided by 50 products divided by 50% reactants, do you see that that would be 1? Okay, so that would be an equilibrium where K, which just compares products divided by reactants, if K is 1, then I know that I end up with equal amounts. So what I want to do is I can share. Would you like to be my volunteers? Okay, so this is just blue. It's just water with a couple drops of blue food coloring in it, but I don't want it to turn your hand blue. So whichever is your writing hand, whichever is your dominant hand, just put a glove on. Okay, whichever one you write with, because that's usually the one you want to pour with. Okay, I'm a lefty, but whichever one you happen to be, no judgment if you're not. Okay, so we were going to represent K equals 1 by having equal sized beakers. So you see that this is reactants and this is products, okay? So this is the starting material. So initially, you always start off with all reactants. Okay? So see, like all of this is reactant to start. So what you are going to do is dip your beaker just straight down, pick it up, and pour it into the other pan.
Straight down like that?
Mm-hmm. Just lay it straight down. Now just pick it straight up, no scooping. So this, pour it in. This would be the forward reaction, right? So forward reaction. Now you lay yours straight down. Nope, you're the product. You're the reverse, right? So straight down, pick it up. Okay, she got a little bit. Pour it back. That's the reverse. Now you do yours. So you can see at the beginning of a reversible reaction, there's more forward. You do it. So just lay down, pick it up, pour it back. Okay, so initially, definitely there is more forward reaction. Keep doing it. So you take turns. You're going to put yours straight in, pour it. You're going to lay yours straight down, pour it. Lay yours. So notice that hers starts getting a little bit less. The reverse reaction starts getting a little bit more. Keep going. And what are you starting to notice about the levels in the pans?
That one, she's taken away.
They're getting closer to being.
Oh, they're balancing?
Right? So once we get to the point where the amount in her beaker is equal to the amount in her beaker, that's equilibrium. Right? So when you get to the point that what you're putting back and what she's putting forward is exactly the same, then that's the point of equilibrium. Same size beakers. So if we look at them, they're pretty close. Okay, pretty close. Forward, do another reverse. And now I want you to like dip them both and hold them up side by side. Yeah, about same, pretty close. That's what I would call equilibrium. But now, do you see then at equilibrium, the forward and the reverse reactions are equal? And since my beakers are exactly the same size, then my pan ends up having equal amounts in both sides. That is when the ratio of product and reactant at equilibrium is the same. So that is when K would equal 1. So K is really just a way of describing how the products are relative to the reactants. All right, so we're going to start over. So in this one, instead of having the exact same size beakers, now I'm putting I always start with all reactants, right? At the beginning of a reaction, everything's reactants. So now, here's my forward reaction, here's my reverse reaction. Okay, so I want you, dip, pick it up, transfer it across, and now you dip, pick it up, transfer it across. Keep doing it. So you do one, you do one. So do you see that her forward reaction is bigger? Okay. So are these going to end up equaling? You're going to end up with more product when you get to equilibrium because she's kind of limited. She can only really move 50 milliliters because of her beaker size. That's going to be her limitation. She can't move back any more. This is going to be when K is bigger than 1. The forward reaction is a bigger amount compared to the reverse. And when I reach this equilibrium, I will have less reactant and more product. Okay, so that would be a K value of where they're not exactly the same. Keep going. But you notice how, Candy, how yours is getting less? Like the amount that she can put in her big beaker is less and less. And eventually, she will pick up 50 mils and you will put back 50 mils. And then there'll be no net change. But notice the levels are not the same. So that is when they say that there is more product than reactant. When you reach equilibrium, that is when K, the equilibrium constant, would be bigger than 1. Most of the time, it's the other way around. Most reactions, K is a lot less than 1, which means that I have a little forward reaction, but most of my reactions are reversed. So this would be if I just switched beakers, right? So if I went and started it over and she had the little beaker and she had the big beaker, I would end up with this. So now when you look, can you see that the volumes are not the same? So that's this. So I end up with more product than reactant because the forward reaction is greater than the reverse initially. So when I reach equilibrium, I don't have the same amount. I end up having more product than reactant. And so she could go back and forth like this all day and I'd still have more product. So K, the equilibrium constant, is greater than 1. Does that make sense? Okay. Thanks. So in this, so think about it like this is where that description comes in. So they were like, okay, you can write an equation to describe products compared to reactants, and that is what they call K, the equilibrium constant. And it's really just the concentration of products divided by the concentration of reactants, but we're really not going to do any calculations with this. We're just going to say it's a comparison. K compares product to reactants when we get to equilibrium. So if the amount of product and the amount of reactant is the same, then that would be like 50 divided by 50, which would be 1. So if K is 1, then I know that the forward and reverse reactions are always the same amount, right, from the beginning. So I reach the point where I get equal amounts of product and reactant at equilibrium. K is equal to 1. If my forward reaction is greater than my reverse reaction initially, then K is going to be greater than 1. And that's not very common. Usually it's the last one. Like when we talk about acids and bases, hold on. When we talk about acids and bases, K is typically less than 1. So here, the reactants predominate, which means that I might have like 1 over 100. So I might have 1 part product, 100 parts reactant. So this K is just comparing product compared to reactant. So it's the top number is product or the amount of your product, the bottom one is reactant. So you see if I have a lot more reactant than product, that just means that the reaction doesn't happen in the forward very much. Most of it ends up staying as reactant. So that's like what you see with a weak acid and base. Remember, like with the acetic acid, only 5% become product. So that would be like a 5 divided by 95% stays as a reactant. So that number would be 5 divided by 95. It would be a number less than 1. So most of your weak acids and bases are going to form ions, but they're going to have a really small K, comparing product divided by reactant. So this is just so like they're going to talk about this, just so that you can pick up, if you see numbers of like 1 times 10 to the minus 5, or 1 times 10 to the minus 10, those are very, very small numbers. Those are really small K values. That means that you don't have a lot of product. Most of what you've got is in reactant. So remember when I told you how acetic acid, vinegar, CH3COOH, when you put it in water, that only about 5% of it forms ions. 95% stays connected, stays as a molecule. So this has a very small K. Product divided by reactant, that'd be like 5 divided by 95. So my number's less than 1, which means that I have more reactant. If K is bigger than 1, I have more product. If K is less than 1, I have more reactant. And K being really small is typical of weak electrolytes. Okay, so in looking at, we like kind of turned around and applied this, the shifts in equilibrium, what happens, how reactions respond to changes in equilibrium. This is kind of a chart that sort of summarizes it, but remember that I said anytime you add something, the reaction shifts which way? Not to the right or the left, it shifts away from whatever you add. So if whatever I add, if I add something, doesn't matter if it's reactant or product, the reaction will shift away. From whatever I added. Doesn't matter if I add reactant. If I add reactant, the reaction shifts to the right. If I add product, the reaction shifts to the left. If I add heat, then it just depends on where heat is in the reaction. But this is the thing, if you add something to a reaction at equilibrium, the reaction always shifts away from whatever you add. Because when I add something, that side becomes heavy. And so the reaction's going to shift away to bring it back into balance. If I remove something, if I have a reaction at equilibrium and I remove something from that system, from the reaction, doesn't matter if it's reactant or product, the reaction always shifts towards whatever I removed. And that's really like it in a nutshell, okay? Doesn't matter if we're talking about reactant or product. This is really sort of, if there's any change in equilibrium, the reaction will shift to try and restore equilibrium. So we looked at this one, so let's look at this one, okay? So what if I add H3O plus? So I have this reaction at equilibrium. Which direction will the reaction shift if I add H3O plus? Will it go to the right or the left? It's going to go to the left, right? Because this is what I add, so it shifts away from whatever I add. What if I remove CH3COOH, or sorry, CH3COO with the negative? So which one am I, find it, you always got to find it in the reaction. So see it's on the product side? Do you see it's on the right? And if I remove it, the reaction shifts towards whatever I remove. So which way will it go, to the right or left? It's going to go to the right. So here is, so here's this. So if I take this out, the reaction shifts towards it. Okay? If I added it, the reaction would shift away from it. Okay? Let's look at another one. This one. What if I add NO2 minus? Reaction's going to go to the right. Because I add reactant, the reaction is going to shift forward or shift to the right. What if I add CN minus? To the left. It's going to go to the left because that's adding a product, so it'll shift in reverse. Okay, so what if I remove HCN? So if I remove HCN, HCN's over on the left side, it always shifts towards whatever I take away. So if I take out HCN, the reaction will shift to the left to try and restore equilibrium. So what if I remove HNO2?
To the right.
That's going to cause it to shift to the right. Now, if I have an endothermic or exothermic reaction, remember that all that means, if it's exothermic, like this example right here, just think of it as being a product. If it's endothermic, then think of it as being a reactant. So the term energy belongs on the side, depending on what type of reaction we're talking about. So remember exo, so this one, this is exothermic. If it was over here, then this would be endothermic. Right? Because endo means I have to put energy in, so energy is a reactant. If it's exothermic, energy comes out, so energy is a product. So in this one, what would happen if I add, this reaction's at equilibrium, what if I add HSO4 minus? Which way will it shift? To the right. Do you see why? Where's HSO4? Is it a reactant or a product? It's a reactant. So it's going to shift away from whatever I add. So that's a reactant, so the reaction will shift away from that. What if I added NH4 plus?
To the left.
Then it's going to go to the left because NH4 plus is a product. So it'll shift away from the product side, shifting back in a reverse reaction. What if I add energy?
To the left.
Yep. So anytime you add something, doesn't matter if I add reactant or product, the reaction shifts away from whatever I add. That's how you figure out if it goes to the right or the left. It doesn't just go to the right or the left every single time. It depends on where that substance is in the reaction. If I add reactant, the reaction will go to the right. If I add product, the reaction goes to the left. Does that make sense? Okay, and then if I remove. So if I remove HSO4 minus, it's going to go to the left because HSO4 minus is a reactant. Whatever I remove, the reaction moves towards it. Think of it like the seesaw. If I take some stuff off of the reactant side, that side gets too light. So I have to shift the reaction towards what I removed to bring it back into balance. So what if I remove SO4 2 minus? And what if I remove energy? So both of those are like products. So if I remove product, the reaction goes to the right. If I remove reactant, the reaction goes to the left. Okay? So we'll do one more next time just to kind of practice the whole equilibrium thing. But really what you've got to remember is you've got to remember this part. This is kind of like the key up at the top. Okay? If I add reactant or product or energy, doesn't matter. If I add any of those things, the reaction always shifts away from whatever I add. You just have to find it in the reaction. Okay? If I remove something, the reaction's always going to shift towards whatever I removed. Just like, yes, I just flip back and forth. Like I've taken my sweatshirt on and off, like I don't even know, like 5 times today. And I'm like, no, I'm like hot. Okay? So here's the connection with the K. Right? So I told you K is just looking at the product compared to reactants. So do you see that there's the products? So these are the products. And do you see that they are listed at the top? These are the reactants, and they don't put water. But these are the reactants, and these are listed on the bottom. So when you think about a K, it's always products compared to reactants. If they're exactly the same concentration, then K is equal to 1. But in weak acids and bases, remember I told you that this is like 95% and 5%. So that means that over here, this number up here is going to be somewhere around 5%. Down here is going to be the 95%. So if I do the math for that, this K is less than 1. So it's really what I was explaining in the previous one, talking about equilibrium constants. Most weak acids and bases have a very small K, okay? 0.001, 0.000001. So really small numbers, a lot less than 1. So in a weak acid and base reaction, there is a reverse reaction as well as a forward reaction. So you can actually describe the exchange of the hydrogen ions in the forward reaction and the exchange of a hydrogen ion in the reverse reaction. So in this one, looking at this, so the first CH3COOH, this is the acid, H2O acts as a base. So if you track what happens to CH3COOH, do you see that in the reaction it loses a hydrogen ion? So it ends up being CH3COO. It loses an H. That's why it's an acid. So remember that acids are proton donors. Think of them as losing their hydrogen ion. I always think of them as just losing H plus instead of the proton donor part because it's just easier to think of them. When I see in a reaction, if I look at this and I look at its partner on the opposite side and I go, oh, that lost an H. And it really lost a H plus, it lost a hydrogen ion. I know that's an acid. Then if I look at water, so if I compare water on the left to what happens to its pair over on the right, I see that it gained. It went from H2O to H3O, right? So I see that it gained a hydrogen ion, and that's what defines a base. Acids lose their hydrogen ions, bases gain. So in the forward reaction, the acid is the thing that loses, it is the compound that loses its hydrogen ion. The base is the one that gains it. But then in the reverse reaction, there's also an exchange of hydrogen ions. So do you see that CH3COO minus, if I look in the reverse reaction, I would say that it actually gains a hydrogen ion. So this, over on the product side, CH3COO minus, going to the left becomes CH3COOH. So I see that it gains a hydrogen ion when it goes that direction. I see that so that's why they call it that. Since it gains a hydrogen ion, it's a base. But they always define the product side as being a conjugate acid or base. So the left side, the reactant side in the forward reaction, you identify the reactants as being an acid or a base. But then on the product side, because those go in a reverse reaction, they also swap a hydrogen ion. So you identify them as being a conjugate acid or base. So in the reverse reaction, the conjugate acid is going to lose its hydrogen ion, and the conjugate base is going to gain it. So in this, H3O plus, when it converts back to H2O, I see that it loses a hydrogen ion. That's why it's an acid, but since it's on the product side, I'm going to call it the conjugate acid. So look at these reactions. Here's the one that, like up here at the top. HCN plus NO2 minus plus makes or forms a equilibrium reaction with CN minus and HNO2. So you know that this is the reactants. And you know that this is the products, right? Because the arrow is what separates them. So what you have to do is look at HCN and find the most similar molecule on the product side. So what does it look most like? HCN, does it look like CN minus or HNO2? Yeah. Do you see that these look similar? Okay. Do you see that NO2 minus looks a lot like HNO2? Okay. So now what happens to HCN? In this reaction, HCN becomes CN minus. So what happens? It loses its hydrogen. So if it loses its hydrogen, it's a what? Acid. What happens to NO2 minus? It gains. So it becomes HNO2. So it gains a hydrogen. And that means it's a base. So that's in the forward reaction. So that's if I'm looking from the left and then seeing what happens on the right. But then remember, in a weak acid and base, I have a reverse reaction just because it goes to equilibrium. So I can look at CN minus and then compare what happens to it when it becomes HCN. So when CN minus goes in this direction, what happens to it? It gains a hydrogen ion. And so that means it's a, this is the conjugate base. Whereas HNO2, it converts to, not to that one, I went to the wrong arrow. It goes to, and so it's going to lose H plus, and that's going to make it the conjugate acid. So really, if you look at a reaction, if it is a weak acid-base reaction and you have this equilibrium, the acid always becomes the conjugate base. The base always becomes the conjugate acid. So look at HCN becomes CN minus. The acid always becomes the conjugate base on the product side. The base always becomes the conjugate acid on the product side. So they kind of pair off. So the acid is going to become the conjugate base, and the base will become the conjugate acid. So knowing that, NH3, which one's most like NH3 on the product side? NH4 plus or SO4 2 minus? Which one looks the most like NH3? Which one looks the most like this? NH4 plus. So what happened to NH3? It gains, so that makes it a base. So it gains a hydrogen ion, so it's a base. So then what do I know NH4 plus is? It's the conjugate acid. The base always forms the conjugate acid. So look at HSO4 minus. HSO4 minus, most similar, SO4 2 minus. And so what happens? No, HSO4 becomes SO4, so it loses its hydrogen ion. So that means it's a acid. So that means SO4 2 minus is the conjugate base. Okay, so the acid on the reactant side becomes the conjugate base on the product side. The base on the reactant side becomes the conjugate acid on the product side, always. Okay, so that's really all you have to do is you just look at the reactant and find the most similar molecule on the product side and figure out, did it gain a hydrogen or lose? If it gained a hydrogen, it's a base. If it lost a hydrogen, it's an acid. And then whichever pair it is, it's the conjugate opposite. So if it's an acid, then it's the conjugate base on the product side. If it's the base, it's the conjugate acid on the product side. So the conjugates are referring to what happens in the reverse. So the conjugate acid will lose its hydrogen ion if it does the reverse reaction. Because remember, this is equilibrium. So we have forward and reverse that's going on. So a couple more. If you see that double arrow, then you know it's an equilibrium reaction. So then look at H3PO4. 4. What is the most similar molecule on the opposite side? Yep. So do you see that this and this are the most similar? And you'll have ones that are very different. Like you shouldn't miss this, you should be able to say, oh yeah, H3PO4 has a phosphate, H2PO4 has a phosphate. Okay, the other ones don't. So then the next question is, did it gain or lose a hydrogen? So it loses its hydrogen, that means it is a acid. That means this over on the other side is the conjugate base. Because H2PO4 gains a hydrogen ion in the reverse reaction. So then if I look at NH3, most similar molecule on the opposite side is NH4 plus. So what happened? So if it gains a hydrogen ion, that makes this the base. But that means over on the product side, NH4 plus is the, conjugate acid. Okay? If you see a strong acid in base, they're not going to do this. So if I asked you something with those strong acids and bases, like with HCl and NaOH, with calcium hydroxide and nitric acid, with these two, the arrow is in one direction. This is a strong acid. This is a, sorry, I have it backwards. This is a strong base because of the hydroxide. This is a strong acid, nitric acid. And what do they make? When you mix a strong acid and a strong base, they don't form a conjugate acid and base. They do what? What were we talking about at the very beginning? Strong acid and strong base make a, what's that reaction called? Strong acid and a strong base. They don't go to equilibrium. They react so that they neutralize each other, and they make a what? So what is the product in a neutralization reaction? A salt and water. So remember that strong acids and strong bases make lots of ions, ions that are corrosive, ions that cause irritation. Calcium hydroxide, nitric acid, not stuff that you want to have come in contact with the skin for prolonged periods of time. But if you take these two and mix them, the calcium will combine with the nitrate, the hydrogen and the hydroxide combine, so you would end up with calcium nitrate and water. These are neutral. So these are not corrosive, they're not reactive. This is just your salt. It's really like a double displacement reaction. The outside pairs and the inside pairs combine. I will not ask you to finish a chemical reaction, okay? But if you see a chemical reaction with the arrow going one direction, then you know it's not equilibrium. Okay, so you know you don't have a conjugate acid and base going on, because when I mix these, they react and I get product. Those products do not reform because they are so much more stable as a salt. Strong acids and strong bases are very reactive. They don't exist stably. If you put them next to something, they want to react with it. So neutralizing acids and bases require that you mix strong acids and strong bases together in order to form a neutral salt and water. All right, so we'll come back and we'll do some of those ones. So this shifting in equilibrium that occurs, it occurs in lots of different types of reversible reactions. So one example in the body is the way that oxygen is carried in your blood. So when you inhale, and that means that helps to pull oxygen into the air sacs of the lungs. So oxygen, oxygen, oxygen. Well, there's blood that flows right past the air sacs of the lungs. The little capillaries, and they have low oxygen. So what is going to cause this to move? If we have oxygen at high concentration, What is it that moves it? It's called what? What is the term that's where things move from high concentration to low concentration? Last chapter. Very end of last chapter. Transport. What passive transport?
Active transport.
No, what passive transport type moves things like oxygen from high concentration to low concentration? Begins with a D. D. Diffusion, right? Okay, so diffusion is going to move oxygen from the air sacs of the lungs and into the blood. So oxygen moves in, oxygen moves in, oxygen moves in. And so this reaction occurs. Hemoglobin, so see this HB plus? This is hemoglobin that is inside of your red blood cells. It will bind with oxygen and it becomes oxygenated. That causes those blood cells to get bright red in color. The way that it binds oxygen is it actually releases a hydrogen ion. So it acts like an acid. Hemoglobin donates its hydrogen ion, it releases it as it picks up that oxygen. And that's allowing that hemoglobin to hold on to the oxygen. So now hemoglobin's got oxygen in the blood vessel, and the blood vessel, then the red blood cell keeps on flowing. So it goes back to the heart, goes to the left side of the heart contracts, pushes blood into your systemic arteries. They branch and branch, and they get all the way to the tissues. Once these get to the tissues, how is it different? Blood vessels in the lungs have low oxygen concentration. Blood vessels, so here's your cells, and we'll say your cells, they have low oxygen concentration. But the blood vessel flowing past has high oxygen concentration because it picked it up at the lungs. So now, as that blood flows by, what happens? High concentration to low concentration, what's going to happen? Diffusion, right? So oxygen is promoted to move out of the blood and into the cells so that the cells can then use that oxygen to make energy. So we want this to happen. We want oxygen to go into cells. As oxygen goes out, that causes more hemoglobin to release oxygen. So if you look at that reaction, when oxygen, the forward reaction is what happens in your lungs. When oxygen comes in, that's like adding oxygen. So remember, if I add oxygen, the reaction shifts to the right, which makes hemoglobin carry more oxygen. But the reverse reaction, like the blue arrows at the bottom, the blue arrows, when oxygen starts to leave the blood and go into the tissues, that's going to promote hemoglobin to break down and release more oxygen at those tissues, and that's going to help to keep that balance. So that allows more oxygen to supply to cells through this equilibrium reaction. So this happens at the lungs. This is what's going on at the tissues. Forward reaction is the reason that hemoglobin can bind oxygen. As oxygen comes in, the reaction shifts to the right. More oxygen, more oxygen, more oxygen comes in, and you make lots of oxygenated hemoglobin. But when you get to tissues where there's low oxygen, now oxygen needs to be released from the blood and go into the cells. So that is going to spur or cause loss of oxygen, shifting the reaction back to the left. And once you go past this, now hemoglobin is like this, right? So you end up with this. In the tissues, you end up with lots of deoxygenated hemoglobin. And so that is why the blood in your veins is what color? Really dark, right? It's really, really like black looking. It's really, if you've ever like cut a vein and looked at it, it's so dark, it's almost purpley colored, okay? They look blue through your skin, but that's just because you're looking at it through your skin, okay? So oxygenated blood, bright red, forward reaction is pushed at the lungs. Reverse reaction in this one occurs because of oxygen leaving the blood and going into the tissues for the cells to be able to use. So this is an example like where we have this equilibrium. that's going on constantly in how you actually transport oxygen in the blood. So now this leads us to the pH, okay? So they wanted to have a way to measure the amount of hydrogen ion or hydroxide ion that's present in the solution. And so studies on water, they realized that water actually does form ions. So if you have two water molecules, there is one of the water molecules can act as an acid, the other water molecule can act as a base. So one of the water molecules can lose its hydrogen ion. So do you see this one? So it can act as an acid and lose, it can lose its hydrogen ion, and it can form the hydroxide. The other water molecule can pick up or gain a hydrogen ion, and in doing that, it's acting like a base. So you see that forward. The acid loses the hydrogen, the base gains. They're the exact same molecule. At the same time, I can have the reverse reaction occur. So since this is an equilibrium reaction, they said, okay, well, what's the K for this? What is the ratio of product to reactant? The K is 0.1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1, 4.
How you know that?
That, just because it's 1 times 10 to the minus 14.
Oh, I thought
That should be a 1. It is. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 13 zeros after the decimal place. So this K, which, what does that tell you? Does that tell you that you have more product or more reactant?
More reactant.
More reactant. K is very, very small. Okay? So this is 1 times 10 to the minus 14. So that tells you very little hydroxide ions, very little hydrogen ions, very little product is made. That mostly water exists as just water, okay? But there is like 1/1000th of a time you might get an ion and then it goes back, right? More like 1/1,000,000th. 1/1,000,000th of a time. It's like, forms ions? No. In fact, pure water does not form enough ions to carry an electric current. Remember when we did that, I had distilled water and it didn't light up at all? So it does make ions, but it's so small that it's not enough to carry an electric current. So you would say water is an extremely weak electrolyte, to the point that you would have to have a sensor to be able to pick it up. But it does make some. So that became the question of, well, if water has equal numbers of hydrogen ions and hydroxide ions, we can say it is neutral. And so a pH scale was devised based on water. And if water makes this many ions, 1 times 10 to the minus 14th, they said we can use a logarithmic scale. We can use a logarithmic scale, which actually takes the exponents into account. So the log of 1 times 10 to the minus 14 is minus 14. So they said, well, we could use that because these numbers are so small. If we use the log of it, it's going to give us a number that's closer to a whole number, 14. So they said, well, we're going to make our scale from 0 to 14. So the scale became 0 to 14, 14 being the highest because that is the K value for water. So the pH of 7 is when you have a hydrogen ion concentration of 1 times 10 to the minus 7. And that is what they found was the concentration for water. Okay, so water forms 1 times 10 to the minus 7th molar acid molecules, very, very, very small. So if I take the logarithmic value for that, that's going to give me a whole number. So ways to look at it, if you have something that is acidic, if you have something that is an acid, that means that it has more hydrogen ions than hydroxide ions. Okay, so a higher hydrogen ion concentration. So that means that my number is going to get closer to 1. Okay, because 10 to the 0, this would be 1. Okay, so anything that is a number greater than 1 times 10 to the minus 7 means I have more acid than base, and that's going to give me an acidic pH. Anything that has more hydroxide ions and less hydrogen ions, comparatively, that is going to be a base. And if they're exactly the same, that is going to be a neutral molecule. And that's what water has. So pure water has equal amounts of hydrogen ions and hydroxide ions, so that's at a pH of 7. So in calculating it, so if you don't have a calculator, you want to grab a calculator. So this is the only other math part. Okay, so the calculation for pH, if you were given an acid and you're given the concentration, I will only use the concentration of a strong acid. So if I have a strong acid, we're not going to worry about weak acids because that's a little more complicated. But if I have a strong acid, like hydrochloric acid, okay, so if I have a concentration, you know that hydrochloric acid forms hydrogen ions 100%. So whatever the concentration of my acid, that is also the concentration of my hydrogen ions. So the concentration of a strong acid is equal to the concentration of the hydrogen ions, H plus or H3O plus, either one of them is fine. So because these concentrations are always a negative exponent, if we take the log of the hydrogen ion concentration, it's always going to be a negative number. So like 1 times 10 to the minus 7th. If you put that in your calculator, and remember how to put those in your calculator. So remember the EE button? We got to go back to the EE button. So in this, you just hit 1. If you want 1 times 10 to the minus 7th, you put 1 EE negative 7. And remember the negative is that little plus minus button down near the equals, not the minus button. Use the negative plus minus button down near the equal sign, and you should see a 1 and then a little minus 0.7 on your calculator. That is 1 times 10 to the minus 7. In fact, if you hit equals, it'll change it into the expanded form, and you can see that it is 0.0000001. That's 1 times 10 to the minus 7th. Okay, so you can use your EE button, but now take this number and hit the log button. So do you see the log button at the top? What do you get for an answer? Negative 7. So to get rid of the negative, you have to take the negative of the log of the acid concentration. So that's why that negative number, that negative symbol is out front. So if you have an old calculator, the ways that you have to go through doing them, if you have an old, in that old calculator, I don't mean like old as in dated, but old like the old school calculators, like the ones that I have. So to calculate the pH, old calculator, graphing calculator, they're different. So if you have an old calculator, you always put the hydrogen ion concentration first, then you hit log, then you make it negative. Okay, so it kind of seems backwards. Old calculators, these calculators can only do functions if you put a number in first. So old calculators, you put the concentration first, then hit log, then the plus minus button. Okay, so let's try another one. So put in this 0.000123436. 0.000036. Hit the log and make it positive. So if I have 0.000036 molar HCl, that's a concentration of the strong acid. So I put that in, I hit log, and what did you get?
I'm just trying to figure out. So we got a regular one. I put log and what, negative?
So if you have a graphing calculator, if on your phone, if you usually use a graphing calculator, you put it in the way it's written. So if I have a graphing calculator, I hit the plus minus button, then I hit the log button, and then I put in the concentration.
There's no plus minus.
So down at the very bottom near your equals, do you have a sign change button?
Negative.
Yeah, that's the plus minus button. So it's like it'd change a plus to a minus or a minus to a plus. It's the sign change. Do you see what I'm talking about? Down here? This. That.
I got it.
Yeah. So that's your plus minus button.
So what?
So hit the plus minus button, 0.00036, and then no. Plus minus button, then log, then 0.0036. Because that's how those 0036 and equals. Nope. I got 4.4436. Yep. So I got 4.443697. Come on. 3697499. Okay. Now I still would have to round that to two significant figures because of my concentration. So I would just say that this is 4.4. Okay. All right. So here, clear. Negative 0.123436, and then you hit. We don't need a negative out front.
No.
Minus log 0.123436 equals. Minus, and then the log function, right? And then 0.123436 equals. So you do it exactly the way the thing is written. So you hit this button, you hit your minus, then you hit log, then you put the concentration, and you hit equals. You do it exactly the way the formula is written. If you have an old calculator, I have to put the concentration in first, then do log, and then do plus minus. So it's kind of like I have to work backwards. And it's just because the older calculators, those calculators, you can't do a function unless you have a number in it. Okay? Try the one that's right there. So put in your calculator, put in 0.050, and see if you can get a pH of 1.3. 0.050 is the concentration. So it says you're given a 0.050 concentration, 0.050 molar HCl solution. What is its pH?
1.3.
You get 1.3? Yes? Yes? Okay. All right. So you want to make sure if you're going to use these on the exam, just make sure that you kind of do your order of steps that you need to use. You always put the concentration first, then the log, then the plus minus. Now, you can go backwards too. So if I know the pH, I can figure out the acid concentration. So if I go from pH to acid concentration, here I kind of have to flip the number. So if you have a graphing calculator, it's going to be different again. But if you have the old school calculator, so the old calculator, if I want to go backwards, I have to put in the pH and make it negative. So I put in whatever my pH number is, make it negative, then I have to hit the inverse log. Okay? If you've got a graphing calculator, you're going to hit second log negative pH.
Second log negative pH.
Yep. If I have a graphing calculator, you're going to have to hit your second button, then log, and then the plus minus button. That's your little minus parentheses button, and then the pH.
Whatever the number is.
Mm-hmm. Okay, so say that I have a pH of 7.83. What is the hydrogen ion concentration? So I have to put 7.83, make it negative, then second log. And that's for mine. Like I can't, it's different if you've got the graph. So I got 1.479 times 10 to the minus 8th.
1 point. Oh yeah, that's what I got.
Mm-hmm. 108,388 times 10 to the minus 8th. Mm-hmm. So in this one, first put in the pH, put 7.83, make it a negative number. You know that little plus minus button down near the equal sign? Put that one, then hit your second button and then your log button, because the second button is your inverse. Okay, that's the inverse button. So the little green button is the second button. Did you get it? Did you get that? So 7.83, make it negative, then hit the second button and the log button and see if you get this. Okay, now the other challenge is sometimes when you do this, you won't get a number, you'll get a number and you're like, where's that? Do you remember to go from scientific notation to English? Do you see on the old calculators, there's number 4 is flow, number 5 is psi, number 6 is ENG, which stands for engineering, not English. I just learned that last week. Okay, so what you would need to do is shift to psi, and it'll put your number in scientific notation. So try that again. Try that again. Go 7.83. Then hit your plus minus button. Then hit second and log. And I got 0.000000015. Okay? But if I want to see all those numbers, go second psi. Do second and psi, which is number 5. Mm-hmm. Do you see then? You see 1.47918. That gives you all of those numbers. And there's the little negative 08. So that would be times 10 to the minus 8. Huh? Oh, it's not inverse. It's, well, I call it the inverse log, but it's the second button. Mm-hmm. The second button is the inverse button. Mm-hmm. Because it's the 10 to the x. So it's the inverse log is what 10 to the x is. So you just hit the second button, then your log button.
Ms. Carmichael, I got it on mine, but when I did my log, my base is 10, so it didn't give me all of that. It just stopped me at 0.000001479. Can you tell me where I do? Because I'm gonna use my calculator because I don't know how to use this when I take my test.
Right. So in that, well, you can't use your phone.
No. I got a calculator.
Your graphing calculator. So to switch it, you have to go into your mode. To switch it to scientific notation, you have to go into mode and choose psi. Like if you hit mode, it'll give you all of these options in a graphing calculator. And I don't know if yours has it in that calculator, but in the other graphing calculator, like the TI 84s and ones that I've looked at, those ones, there's a mode that you can switch from regular, standard to scientific, so that it'll put in scientific notation for you. So that one, you would end up rounding that one. I would keep the 1, the 4, and the 7, because 7.83, 3 significant figures. So I would round this to 1.48 times 10 to the minus 8. Now, if you want to go back from psi to regular expanded, you hit the second button and number 4, and that's flow. I don't not really know what flow means. I just know flow is like normal. Yeah. Number 4 is flow. Number 5 is scientific notation. So you can go back and forth with that. So if you just hit second and flow, It's at 0, so it doesn't show that exponent button. But if you go second to number 5, the exponents always show up, the little 0 above. And remember, those 2 little zeros tell you what the little exponents would be related to. All right, so let's do a couple of them. So what is the pH of a hydrochloric acid solution that is 2.65 times 10 to the minus 5th molar? And we can practice a couple more of these ones too next time. And if you get that one, what is the concentration of a hydrochloric acid sample with a pH of 1.68? So remember, inverse. Inverse is not inverse. This should be, for you guys, it's what looks like the second button. I just always learned it as the inverse log. I don't know, I haven't done it yet. This is what I got. 4.576754126. Is that what you got?
I'm gonna figure it out.
Yay. Okay. Yeah, and it's really just a matter of like making sure you put your steps in. If you want to go from concentration to pH, you put in the concentration, hit the log button, then the little plus minus button. How many significant figures should my answer have? 2.65 has? 3. Mm-hmm. So remember then, you always just look at that measured number. Remember the exponent parts doesn't matter. It's everything that's in front of that exponent value. So 2.65, that's 3 significant figures. So 4.57 would round to. Mm-hmm. What? Yes, did you get it? Did you put it in your calculator and get it? Remember, use your EE. So if you're going to put it in your calculator, put 2.65, EE, 5, and make it negative. Right? So that's half of the problem, is making sure you know how to put exponents in. Okay? So this 2.65 is 2.65. Then that EE button, then a negative 5. So when you put it in that calculator, it should look like 2.65, and then the little 0.5 should have a negative in front of it. Yes? Then hit log.
I think I'm just always trying to get the 10.
Yeah, you don't need the times 10 to the, because EE means times 10 to the. So that means you drop that whole part out. So just put 2.65 EE minus 5, and then hit the log, and you should get a negative 4.576754126. Yes? Okay? So like maybe add that to your instructions, okay? Numbers with exponents, you put the number in, EE, and then whatever the exponent value is. Did you figure it out? Well, where's yours?
I'm trying to change my settings on it though, because just do it straight.
So you're going to go, so you cleared, negative log of 2.65, 2.65. Where's your EE? Second, EE, 5, 1, minus 5. How do I delete just 1? Oh, you can do 6.5. I put 3.5 in.
That's what I did. I had to do
Negative 2.65. Second. So write those steps down, okay? Because you can use you've got an EE button just like this one. That makes sense? All right, so now see if you can do the other one. Then we're going to quit because it's like time. Okay? So did you get it?
No, it went off, but go ahead, I'm gonna try this.
Okay, so in this one, if you know the pH and you want to figure out the hydrogen ion concentration, you take, if you've got an old calculator, put in 1.68, make it negative, then hit second log. If you have a graphing calculator, you have to do second, log, plus minus, and then the pH. Okay? So in this one, put in 1.68, make it negative, then hit the second button and the log button. I just put new batteries in this pen last week. That's all and I knock it on the desk, it like kicks back in. It's okay. Did everybody get that? 2.089296131 times 10 to the minus 2. Okay. Do you get that? Like when you look, can you convert what the number that you see on your screen? You can convert that because yours doesn't have the times 10 to the, it just has a little minus 0.2. So you've got to remember, you got to put the times 10 to the back in. What do I have to round that to? Yeah, because see, this is 3 significant figures, so 2.09 times 10 to the minus 2. And that's actually molar because it's a moles per liter concentration. Okay, so concentration with pH is molar. So you don't have to, I'm not going to make you like calculate any moles and liters and such with it, but that's the concentration, is it's always given. It's not given in percent, it's always given based on molar concentration. Okay, all right, so we have a couple more. So there are ones that you can practice the last couple of pages, or not the total last couple of pages, but there's a couple more pH practice ones that we can do on Monday night to finish up. All we have really is I want to talk about like what the pH scale is in reference to general things that you know of. And then I want to talk a little bit about buffers. And then we're going right on to chapter 10. Okay, so that we should be able to get into chapter 10 on Monday. Do remember that you need to bring your